All right, welcome back. Let's get straight into it, shall we? Alrighty, here we go. So we have calculated the commutator of the time derivative and arc length derivative. And now I'm going to show you how we can leverage that to calculating how the curvature changes with time. All right, so here we go. Evolution equations. First, though, we need to look at the tangent vector. Okay, so this is the time derivative of the tangent vector. Now, the tangent vector has unit length, so the length is not going to change, but the direction of the vector will change with time. Okay, let's have a look. First thing we do is write down what the tangent vector actually is. And I might not have mentioned this before, but it's nothing more than the arc length derivative of gamma itself. Now this makes sense because, if you're moving along the curve and you differentiate the vector of the curve with respect to the length along the curve, then that will give you your unit tangent vector. Okay, but now this expression, ddt dds, should look familiar. It's part of the commutator. Okay, so what we do, okay, now I made a little typo here. What we do is we add and subtract. Let me just fix this up. There we go. We add and subtract ds dt, so we don't change it at all. This is a very common trick that mathematicians love to do. Add and subtract the same thing. But the reason for doing it is that this first pair of terms is the commutator and is very, very nice. Okay, this is applied to gamma. Okay, so we can write that as the commutator. And it looks like this. Now the commutator is, okay, so I'll write down this other bit first. Okay, this is the ddt of gamma that we know from before. The commutator itself, you can see it here. It's just minus kf plus ts, and then there's a ds operator. Now that ds operator is going to hit gamma and turn it into tau, which is fine. So let's see that in action. Okay, there it is, minus kf plus ts, and then that'll be tau. Okay, and then we've just got this bracket, and I'll leave the derivative unevaluated. This is the same thing. I just wrote it differently because why not? Keep things interesting. Variety is the spice of life. Okay. Now, on this next line, we're going to get a few bits and pieces of cancellation. So, for example, when the s derivative hits the t, you can see you're going to get ts tau. Here you've got minus ts tau. They cancel out. You get quite a few cancellations. Okay, now again, when the s hits the nu, this is the Greek letter nu for normal, we're going to use this equation. Now, if you are confused about where on earth these equations come from, it's actually very easy to show this. You just differentiate the frame equations and use, well, you just differentiate the normal and you see that its derivative is perpendicular to itself. Right? Because its length is 1, you differentiate that, and you get nu times nu s equals 0, which means that nu s is orthogonal to nu, which means it must be proportional to the tangent vector. So you write it in that expression, in that form, as proportional to the tangent vector, and then you use the fact that tau dot nu is 0 to move the derivative with respect to s back over to the tau. You pick up the minus sign, and tau s is the curvature vector. That's how it works. Anyway, if you want to try to follow that with writing, I leave it as an exercise to you, interested audience member. Okay, so once you do this, you get minus k tau, so then that's going to kill this term, right? Because of the minus here, minus minus makes a plus, and so that will completely eliminate this bracket, and you'll only be left with two terms. Okay, so again, we use this tau s as k nu. Again, it's the same method as I just described as for the normal vector, but easier because tau s is just the curvature vector by definition, so it is k times the normal. Anyway, okay, so you're left with this for the time evolution of the tangent vector. Okay, big deal. So what? We want the curvature. How are we going to get the curvature? Okay, well, I'm just writing this down again. Now, where did I start writing? Give me a second. It must be here. Yeah, here we go. All right, so we want the curvature. We're going to start with the curvature vector. The reason we start with the curvature vector, by the way, this little bracket, it's because there's some weird bug with, repeating old operations, and there's supposed to be an evolution equation written here, but there's not. Anyway, I think it'll be fine. Don't worry, I'm here to explain. Okay, so we're differentiating the curvature vector with respect to t, which we've seen before. It's just this expression here. And now we want to move this through. Now, we do the same trick of adding and subtracting, of adding and subtracting the same thing to turn this into the commutator. Okay, we'll see how that works. Right, so this is the commutator. Okay, this is applied to tau. Tau is just ds gamma. Okay, so that's, well, there should be a tau here. I'm sure I'll fix that up very soon. And then in this remaining piece, after the terms cancel out, you're going to get DDS of DDT tau, right? Because these swap. So that goes there. So it'll be DDS of DDT tau, which is what this is. Cool. Now we know what DDT of tau is because we just calculated it. It's that. Now that's actually a pretty hairy expression because there are so there's two groups. So there's a group of 3 terms here, and there's a pair of terms here. So when you take the s derivative, you're going to actually end up with like 5 terms. Anyway, lots of them will cancel out. Oh yes, now I've fixed up the little tau there. Okay, so we're applying the commutator to tau. It's just this expression, and then there's the s derivative, and that applies to tau, gives you the curvature vector. Okay, the curvature vector is just k times the normal. Just write it in like that. Okay, now this other term, we're going to break it into 2 pieces. First, we differentiate the normal. That'll give us curvature minus curvature times a tangent piece. There's the tangent vector, and there's the coefficient. And then we're going to have the s derivative on this bracket. And that will be a normal piece. Okay, so in this way, we've worked out already in what direction these terms are. So this is a normal component, this is a normal component, and this one here is the tangential component. And they're really not going to interact much. Because there's no more derivatives on vectors, so these are just not going to interact. They're orthogonal. So I moved around this bracket, which we can't even see, but anyway. I wonder why we can't see it. Is there? I'm not sure. I think it's my mistake. Anyway. All right, let's keep going. So basically, let's collect together the normal terms. So we've got a minus k squared f. We've got a kts minus kts. And then we've got a plus kts, so that'll cancel. We've got a kst, which is not going to cancel, and a minus fss. So let's see all that come into being. Some are new terms. Okay, so there's all those things that I said. And those two kill each other, and the rest stay. All right, and then you're going to have the tangential piece, which nothing happens. And so that's it. That's the evolution of the curvature vector. What about the curvature scalar? So for the curvature scalar, use the definition. It's just the projection onto the normal of the curvature vector. Well, it's given by this inner product. And the time derivative passes onto both terms. But when it hits the normal vector, you just get back a tangential piece. The tangential piece is orthogonal to the curvature vector. So there's no term when it hits the normal. It will just be 0. Right, so I just put plus 0 there because I want to remind myself that there's no term there. Okay, and now this term here is very easy to calculate because we've got the derivative, and so all we need to do is write down this normal piece. And that's it. So you've got some kind of a second derivative on the speed. Then there's a curvature contribution, nonlinear curvature contribution, and then there's this curious tangent speed term. Okay. Now, let me see. What I want to do next, I'm basically finished now for this video, so let me just fade myself back into huge mode. For the next video, I'm going to show you something really cool. It's something a little bit special, and yeah, I hope you'll join me for it. Okay, thanks for your attention. Take care, and I'll see you in the next one. Peace.